Hello, everyone. So my talk is called Rust Access All Areas, because one of the big movements for the language Rust last year was we actually finalized the ability to deploy Rust on basically any target, theoretically. I'll talk about the practice in a second. But first of all, I have a word about Joe Armstrong, who was mentioned this morning, because he has been very important for me. I have read Programming Erlang in 2009, and what I really liked in the book is how he insisted on how concepts strictly applied can solve problems. In the case of Erlang, it's shared nothing and message passing, and how strictly applying them makes a lot of problems easier by relying on that the language always does this. Yeah, that's kind of the point. Sometimes you have to invent a language for that. And Rust comes pretty much out of the same vein, that if we want to solve a couple of fundamental problems, we need to invent a new language for that, instead of trying to paper over in the languages that we have. So who am I? I'm Florian. You can find me on Twitter and on GitHub. I have two companies, one that runs infrastructure and another one that's called Ferrous Systems, which is Rust consultancy. I am a Rust programmer and trainer. You can find me on Rust Experts. I'm also a Mozillian. Sometimes people think, because of my activity in the Rust project, I am employed at Mozilla. That's not the case, but people who are closely aligned with Mozilla's mission are usually called Mozillians. Previously, I did 10 years of Ruby community work, so there was a point where people stopped referring to me as the Ruby person in Berlin and then moved to, hey, that's Rust Florian. I personally started learning Rust in 2013, mostly out of curiosity. It was a new language. It was still in research work. I co-founded the Berlin user group. I then started organizing two of the largest Rust conferences, RustFest and OxidizeConf, which is focused on embedded hardware. And I'm a project member since 2015, most of the time in the community team. Recently, I started leading the website team. I'm now in the core team as well. And I've got a quick question to the room. Who here has been exposed to Rust? Who has worked with Rust? OK, not so many people, because I'm going to give you a detailed explanation of what it is. Also, I have a couple of endorsements. I gave a talk about Rust at GOTO 2017, and the best YouTube comment is, I don't trust any programmer that deliberately uses Ruby and Java. Yes, I still use Ruby and Java for great effect. So please, if you don't immediately start using Rust, that's all fine. There's tons of very good software around. Just quickly about the Rust project, I'm presenting the work of 180 team members and over 5,000 contributors over the last years, and that's just the core repositories of the language, culminating in a large release in December last year. Rust itself was released in May 2015, so we're talking about a language that's roughly 4 years old, and a little bit older. So what is Rust? Our current claim is it's a language empowering everyone to build reliable and efficient software. Before the 2018 release, we said, well, there's 3 things that are important about Rust. First of all, the language is safe. Second, it's concurrent. Third, it's fast. The problem with that is those are very language-level concerns. Also, what is safe is something that people can have long Twitter fights about. And we changed that. Nowadays, we say the 3 important parts of Rust are performance, reliability, and productivity, all of these 3. And our mission is to bring that to everyone. It's literally in the claim. So we need a language that scales up and down, so it should work on small targets, down to microcontrollers, up to server-level targets, big data applications, databases. So it must provide high abstractions and low abstractions, also very cheap abstractions. They must be useful, but they must also be peeked through, because if we want to work close to the hardware, we sometimes need to rip them open and work with what we have on the inside. And they should cost nothing. The problem with the thing that's called zero-cost abstraction is, if we're talking about a zero-cost abstraction, what we mean is you couldn't hand-code it better yourself. We built you an abstraction that does the thing that is the most efficient. If the abstraction does not do exactly what you need in that case, it might still cost you something. So maybe another approach is better. But also, ergonomics and care. We have a unified tooling for all of those targets. We have extensible tooling. So if you need something for a specific use case, you can plug into the current tooling and make it do what you want. And we have a very strict backwards compatibility strategy. So the problems to solve that I want to talk about is memory safety, in this talk, resource consumption, resource handling, concurrency and parallelism, dealing with external data, resilience, and integration into existing code. So let's get started. The talk has in the title Rust 2018, access all areas. So just to quickly clear up what Rust 2018 is, it's a new language profile to enable all of the above. We shipped it in December 2018. It was not a breaking change. The Rust compiler still understands old Rust, and you can mix and match libraries. If you opt into the new profile, the language is a little bit more ergonomic. Rust in itself is a C and C++ competitor. As a language itself, it lands somewhere in the middle, that is statically memory safe. And it has features that also make it competitive with higher level languages like Scala, Java, or, for example, also Go. From its model itself, Rust is a native programming language. It's a values and function language, much like C is. And it comes with no notable runtime. So it has no active runtime, it has no garbage collector. Everything that I present in this talk is actually being resolved by the compiler at compile time and not during runtime. Still, it is memory safe, so it looks a little bit like a garbage collector language. It is a generic language. I won't introduce that. I assume everyone here was exposed to Java, and I won't go into higher detail than that. We use the same syntax, so it should be kind of natural. And it has detailed error handling and no catchable exceptions. It's a very, very detailed language. It's kind of like, what if we had a language that's a nitpicker, but in a good way? We usually call the compiler a complainer. We might also call it an Iron Maiden, but I don't know. So let's look at a code example quickly. So he said Rust is a structures and functions language. So we have a data structure here with 2 integers inside, exactly 32 bits, so I know the size of it in memory. So I can talk in Rust directly about memory layout. I can just construct it. I can allocate it on the heap. That works in Rust by a special type that's called box. There's special types that heap allocate. So Rust is a language that differentiates between a stack and the heap. But there's nothing more that I need to do. What happens here is the moment this program ends, it actually starts deallocating all of that memory and then quits the program. And that works through a system called ownership. Any value introduced into a Rust program is exclusively owned. And this ownership can be moved. So for example, I can't pass it into a function. But if, for any reason, this value runs out of scope, it is dropped. And this moment is clearly defined. The moment is exactly here, because that's the end of the scope. That's the moment the deallocation happens. So there's no garbage collection happening that might defer that. It will actually happen at that point. And that can be used for great effect. One of the misunderstandings about ownership is that it's just for memory handling. It is actually very, very useful for any kind of resource handling. So all Rust values have a trackable region in memory where they're active, and that means they can be used for resource management because I know when they become inactive. And ownership manages resources. Memory is always one of them, but it doesn't have to be. One example for that is a file. So if I have a function that reads a file, I just pass it a path, and I get a string back, which is the contents of the file. I'll talk about that results thing in a second. I open the file, and because I don't return the file, I actually don't do anything after reading it. The file will automatically be closed. And that's kind of this resource handling semantics, because I can attach to a file pointer, oh, if it runs out of scope, also call close on it. The question mark here is our error handling operator. Just quickly about that result, Rust has no exceptions. What we use is we use a result type that is in something that we call an enum. It has 2 so-called variants, OK and error, which signal the thing that you wanted to do worked or it didn't. And if I return one of them from a function, I actually ask the caller to, before actually handling the data, checking, hey, was it OK, or do you actually have to handle an error? So results are plain data, like, for example, also in Go or other languages. What it disallows me to do, if I have another function, the implementation is pretty unimportant. That's print file and close. But the important thing is it takes a file, it reads it fully, and because it lets it drop out of scope, it closes it. So what happens if I try to call this function twice on a file? What happens is I get an error. What it tells me is, oh, you moved ownership. You called a function on this piece of data, gave away ownership, and then you're trying to call it again. That doesn't work because you don't own it anymore. Practically speaking, what I just made sure is that the second time I call this function, it actually gets a valid file pointer. If I wouldn't do that, the first call to it would succeed because it can actually read from that file pointer, close it in the end, and the second call would not succeed because the file pointer has been accidentally closed in the meantime. Just as a comparison how that works in other languages, I'm picking Ruby here because of being an old-term Rubyist. What Ruby has a file API that uses a closure to make sure that if you call file open and you then execute this closure, it calls close in the end, so that you don't forget closing files and having dangling file pointers around. That can be circumvented. Because what I can do is I can somehow, because Ruby is a garbage collector language, so I can take any amount of references on any kind of data. So what I can do is I can do file open, and I can say I want an iterator over each line of the file, return that, and oops, that doesn't work. Because the definition of that closure was, once the closure ends, you close the file, and then I'm trying to read from it, bang. This is obviously a simple example. No one would write that, but slides only have so much space. That's also the annoying part of it. If you run into such a bug, it's usually a 1,000-line code base, and then it's hard to figure out where you accidentally closed it. So what happened? We're referencing through the file through an iterator. We moved the iterator out of scope. The file was closed. We tried to iterate. Bang. Let's try that in Rust. We can have a look at the book, and it says, oh, well, Rust has references. And we can try to also get a similar situation where we set up a reader that references the file. This is the referencing operator. &mut is a special kind of reference to which I can actually mutate the end. I come to that. And so I open that buffer reader, and then I'm returning the reader. This actually doesn't work. The compiler will tell me pretty clearly, cannot return value referencing a local variable called file. Because with the rules that I laid out, file must be closed by the end of this function. So we're referencing the file through this reader, kind of a similar pattern. We're moving the reader out of scope by returning. The file is closed. Scope ends. The compiler detects this as illegal. References in Rust are subject to a system called borrowing. References cannot outlive what they borrowed from, so I always have to reference valid memory. And mutable and immutable references cannot alias. So I showed the &mut. There's also the ampersand reference, which doesn't allow me to mutate through it. And the important thing is, if you have a mutable reference in Rust, you can also be guaranteed that it's the only one everywhere in the program. So if you have a mutable reference, there's no other part of the program that can actually currently even read that memory. References are always valid, much like in C++. And the interesting notion here is mutable state in Rust is allowed. Shared state in Rust is also allowed. But shared mutable state is not allowed. And that's the problem that we're usually running into in parallelism and concurrency. And we're also seeing a thing here talking about illegal states. Files in Rust are defined in such a way that they are always open. If you have a file type, it's always open. So Rust gives you methods to make illegal states irrepresentable. Even if you want the file API that represents both open and closed, you have to use a different one that models these states appropriately and gives appropriate API. In contrast to that, the scope with closures approach that Ruby has and other languages have as well, are just about not forgetting to call the close call on a file. But they still have closed file pointers, which are often not very useful. So how do we get out of that? It's actually pretty simple. We change this. It used to be &mood file here. We change this to file and don't reference the file. What happens then? The buffered reader takes ownership of the file, wraps it, builds a buffer around it, and then I can pass both back from it, and then I can, for example, iterate over the lines, print them out with line numbers, or whatever. So pretty often in Rust, that's something that people often run against. If they can't make a reference valid, probably they shouldn't reference, but instead pass values around. That's what we're doing here. We're going back from trying to pass out references to actually passing values around. That's important here. Buffered reader now owns the file, so it's also the unique owner of the file. So it can also be sure that no one else is currently referencing the file, mutating it, writing to it, or whatever. And that's a thing that happens pretty often in Rust. There's a lot of APIs that come in three things: owned, borrowed, mutably borrowed. These are the three things that you hear most about. For example, if you talk about iterators, pretty simple concept. I have a collection, in this case a vector 1, 2, 3, and I want to iterate over it. And there's three ways of actually doing it, which is first of all the owned iterator, which again closes over the collection. You completely forget what collection it was. The only thing you get out is I can iterate over it. And then you iterate over it. And once the iterator drops, all the data that it closed over actually drops as well. This is what it means to take ownership. If I just call iter, I will get the immutably borrowing iterator. So I can borrow, I can iterate over that vector as much as I want. I can actually get an infinite number of these iterators at the same time, because they can all be sure that the data is not being manipulated and keeps at the same length and everything. And I also have a mutable iterator where I can iterate over and add +1 to each of those numbers or whatever. And there, the guarantee applies that if I have this iterator, I know that I can mutate the collection, but no one else can see it. So there's no sharing of this mutable state at that moment. So before that, if I had immutable references or immutable iterators active, I would have to remove them all before actually starting with this. And this relates nicely to parallel processing. So we have quite a number of great frameworks for parallel programming that also work on very, very small devices. They are mixable with concurrent approaches, so we do allow parallel and concurrent programming in the same language. But all that is safe from data races, because data races happen in the moment where I can observe someone manipulating the memory. Basically, the problem is I have an immutable reference, I read it, someone manipulates it, and then I read it again, and it's something different. But I have an immutable reference. What's that? Like, the guarantee of an immutable reference in Rust is the value that you're referencing will never change while you have that reference. And just to show how this works, this is, again, the iterator API. I have another collection of i32, 32-bit integers. I just want to sum them all up. I want to square them and then sum them all up. If I want to do this in parallel, there's actually a library that allows me to just say, this iterator is now parallel, put it on a thread pool, start running it. It's kind of boring, isn't it? It also gives a couple of additional options, like this is the convenience option with a background thread pool where it will just be applied to. You can also say, I want a specific thread pool to be used or whatever, so you always got the option to move out of those defaults. But other than that, that's currently it. I'll get to another detail of that in a second. But currently, if you want to parallelize Rust code, there's very, very easy APIs to do that. There's two large libraries for doing that. If you ever want to do, if that's the way you want to get started with Rust, there's Crossbeam and Rayon. Crossbeam are all the base types that you want for any kind of parallel processing. Several methods for mutexing, fencing, and whatever, thread pools. Rayon is a library that provides these parallel iterators quickly and easily. If you talk about concurrent programming, that is, things like Erlang does it, or for example, Node.js. So you have an event reactor potentially on a single thread or on multiple threads, where you don't have thread-based scheduling, but actually cooperative scheduling between all the units. We have that as well. Also mixable with parallel approaches. The other way around works as well. Also safe from data races. What Rust allows you to model is if you have any kind of concurrent unit, say a thread, a task on an event reactor or whatever, it allows you to model which part currently owns what data. And that works independent of the concurrency or parallelism implementation that you're currently using. I'll show how that works in a second. Currently, concurrent programming in Rust looks like this, because it's completely based on standard Rust API. Anyone here doing JavaScript with promises? Yeah, basically the same problem. So we have a futures type or a promises type, but the only thing we currently have is methods on it to combine them. So actually, each of these things in for each B2End, and also here, are small concurrent subunits, and you need to know the actual names of what of these things are concurrent actions to understand what they do. Also, you need to use these kind of combinators to combine them in the right way. That works. It's verbose and very error-prone, which is actually why we are removing that, or we're moving towards an async await syntax, much like JavaScript has it. So if you have a look at this, you have this for each combinator that takes a function that has a specific behavior, how for each works. This is actually going to be replaced by a while loop that just awaits on. Like, this is a small TCP server. What it does is for every incoming connection, or for the incoming connections, always take the next one and wait for the next one. That's the operation that it's doing here, and explicitly spawn off every connection handling as a second task, or as another task on our current event reactor. You don't need to understand the full density of it. It's just having a special syntax for this use case makes code much, much easier to read. The interesting thing about the async await syntax, again, is you can pick the concurrency pattern that you're using. And the nice thing about being able to pick the concurrency pattern, and especially implementation, is that you can choose the one that's right for the device that you're currently working on. An event reactor that's working on a server can just waste a couple of megabytes of memory, you don't care, and just for performance reasons. Something that needs to work on a small device must obviously use an implementation that's much simpler. The async await syntax in itself comes with no actual cost. The only thing that comes with the cost is the actual reactor that you need to use to drive it. And that's pretty unique, that we have a syntax that's independent of the library implementation that you're using. So you wouldn't need to replace the runtime system, or you wouldn't need to replace kind of the Rust implementation that you're using. What you replace is, I choose a different library from our library host, and then just use that one instead. There's a couple of libraries around this. The most prolific one currently being Actix and Actix Web. Actix is an actor framework, much like Erlang is, and Actix Web is a web framework implemented in it. There's lower level ones. There's two called Tokyo and Romeo, which are just the bare reactors with a little bit of a platform on top. And a thing that we're currently producing within the project, Rust Async, is our async working group called Runtime, that actually puts a facade on top of all of that to give you a unified interface for the most basic functionality. There's a little bit of magic behind this. Every value in Rust has two additional properties, and those are send and sync. Send means that data can be passed between concurrent units. That's much like I could take a piece of data and can send it to another thread. The first thread will not have it anymore. The other one have it. And sync means I can pass it between concurrent units. And both properties are independent of the parallelism and the concurrency library in use. This is a motivating example. For simplicity's sake, I'm just going to use threads here, but this also works in any other kind of situation. So I have a counter, classic counter problem. I spawn 3 threads, and I try to have every of those count once. The problem is, because counting on a processor is I read the data, I manipulate it, and I write it again to memory, there might be a race condition. So programming is, or multi-threaded programming is one of the only ways to actually make 1 + 1 + 1 be 2. And this is what happens here. Luckily, the Rust compiler actually tells me that that doesn't work. In this case, in the initial case, it tells me what a thread expects. It actually wants to take ownership of all the data. Now, the problem is I can only pass on ownership once, but I want to spawn 3 threads. Doesn't work. It actually tells me here, value moved into closure here in previous iteration of the loop. So it understands that we iterate multiple times, and it knows that the first time I'm calling thread spawn, the value is already gone. So what I need is actually multiple ownership, and Rust provides ways of doing that through smart pointers, much like in C++ or other languages. And a standard smart pointer in Rust is the ref counter. If I want ref counting, I can have ref counting. I can construct a ref counted pointer around a piece of data. This is the API how I get a new handle on that ref counter. So I get a second reference. And then let's try. Also doesn't work. Why? Because the standard ref counter in Rust is actually not synchronized. So I might have the same problem just on the reference count instead of the actual data that I'm pointing to. But Rust detects that. It tells me it cannot be sent between threads safely because it's not sent. That's where that property comes from. OK, let's dig a little bit more through the API and figure out if there's a synced ref counter. Yes, there's a synced ref counter, which is the ARC, the atomic ref counter. And let's try that. Same API. Doesn't work. Cannot assign data to an % reference. What's the problem? The problem is I have multiple access points to that data through the ARC. And then the borrowing rule applies again. You cannot get a mutable reference out of that because there might be other people watching. So the last thing I need is a mutex. Because the mutex does exactly that moderation. It makes sure that there's always ever one part of the program currently holding a mutable reference. That works. And interestingly, if you lock a mutex, what you get back is something called a mutex card, which represents, hey, you have currently locked the mutex. And that one, again, there's no ampersand here, is handled through ownership. That means I don't actually have to think, because it's a resource. Your lock is a resource. So I take a lock, and I let it run out of scope here. And the moment I let it run out of scope, it gets immediately unlocked. So I also cannot forget unlocking the mutex. So the compiler has just guided me through a refactoring that usually is pretty dangerous. I take a single-threaded piece of code and rewrite it as a multi-threaded piece of code. I need to make sure that all the data that I access to is properly synchronized and never vanishes out of memory as long as people still need it. It's a classic parallel programming problem. The vanishing out of memory is not a problem if you're working in a garbage-collected language. The one properly synchronizing is still a problem. Let's move on to a little more practical examples. So Rust is used for actually a lot of CLI programs. Anyone here using VS Code? If you ever use the search function, you're using a Rust program. There's a certain subcommunity of the Rust community that wants to make string processing as fast as possible, and there's a lot of outcome coming to these kind of areas. So the nice thing about writing CLI programs in Rust is similar to, for example, if you write them in Go, they're shippable without having people to install a runtime, Python 2.7 or whatever. It's memory conserving with a very, very fast startup time because it doesn't come with a runtime. There's libraries for very fast and convenient parsers. Pretty often CLI programs I use to munch through CSV files, JSON files, whatever. You have a free choice of concurrency patterns. If you want to interact with an API in the backend, probably you want async I/O. If you just want to churn through a lot of data quickly, you probably want a thread pool. And ownership makes this external resource management, hanging around with files, making sure that, for example, all your backend requests are appropriately closed and whatever, pretty easy. But there's also conveniences that the Rust programming language provides you, which is it has ways to allow for structured code generation. So for example, this here is a struct, but through a library called structop, we turn it into the definition of our CLI interface. What the derive does, it looks at the struct and says, there's a command line argument called pattern. It has to be a string. It has to be present, because there's no null in Rust, so that one has to be there. This here is a parse buff. How do you get a parse buff? I can tell it, actually parse it using a standard library functionality. The usage is much like I previously described. The same thing is used for serialization and deserialization. There's a serialization and deserialization framework called SERDE, which we can use in much the same way. We can say we have a point x, y, and we want to have it serializable and deserializable, and then we can actually choose the format we want to serialize and deserialize it to that's independent of this machinery here. And here we say we want to serialize it into JSON and back. The nice thing here is this can error. Like reading a JSON file that might be incomplete, might have additional fields, might have less fields. And so there's always a result coming back. So you need to check if that was actually valid data. So it uses the type system to understand, well, did I even get a valid JSON file here? All that can be configured, just to be clear. So what do you do if X isn't present? In this case, I choose the default, which is null. And I also say, please, in my JSON format, it's called point lowercase, so use that. Which naturally brings me somewhat down the stack. A lot of these programs nowadays are actually deployed on small devices. The first place to go to if I want to go smaller is usually embedded Linux, my router, my IoT gateway, an industry control system. We have seen Rust there. There's people talking about putting it on cars and people researching on that. So embedded Linux is at a lot of places. There's always the conversation if embedded Linux, a lot of people don't consider embedded Linux kind of embedded because it's a full-blown operating system. Still, it has a lot of it brings you into a lot of the problems that start with smaller devices. The first one is cross-compiling. Cross-compiling isn't actually a language concern. It is a language concern in the sense that our standard lib is written in a way that we want to make sure that we can support as many targets as possible. And if the standard lib can't support it, you can at least slice it in pieces where you can, for example, support parts of it. So for example, our memory allocation library is also available as a single library. But the process itself is easy. We give you appropriate tooling, and all tooling in Rust is aware that something like cross-compiling happens. Rustop is a tool that we use to manage Rust compilers and choose the version that you want to have. But it's not just a version switcher. It also, for example, manages targets for you. So if I want to compile for Arch Linux with a Moodle libc, I can just download that from actually our project's hosts and use Cargo, which is a build tool, to build whatever we have over to one of those targets. I need the platform linker and libc available, which is usually, if I, for example, compile towards OpenWRT, I need to have the OpenWRT SDK in my path, and I need to make sure that that is there. Still, from our side, the tooling is as complete as possible. And further down the stack, last year we finally unlocked running Rust with all of those features that I just shown on bare metal embedded, so tiny devices, NRF controllers, and all of these. So that meant a lot of the stabilization of all low-level details, replaceable error handlers. How is the main function called? I use that main function all the time, but what's around the main function? What happens when the program quits? Most people don't care. People on bare metal devices actually care. So it gives you great support for all of these safe patterns on embedded devices. It relies on existing tooling. It should be considered young, but solid. Like, it is done. We have backwards compatibility now, so we can start writing libraries. This is what it looks like if you just want a simple program. The important thing here is it is a no main program, so it actually doesn't have a main function. We're going to write that all ourselves. It doesn't use the standard lib. It uses an external crate for, in this case, supporting Cortex-M processors. The RT is, this is the runtime for a Cortex-M processor, so we want to actually boot and finish the processor if we want to. And it writes its own main function and marks this as entry. Here we're using code generation again through this attribute to actually do the setup of this is how you actually start the board, and this is how you shut down the board, and everything will be generated for you, and then it will be called into that main function. This does, it just loops, just does nothing. So the machine works, but it does nothing. I'm going to skip that time. But we're still using Rust semantics there. Especially the embedded working group has come up with a lot of interesting usages of, for example, mapping a device access to ownership. Because I have the same problem again. I don't want two parts of the program to use the same port at the same time. That's an ownership problem. I want unique ownership. It uses these meta-programming facilities that we provide for convenience, like being able to mark a function as an entry point and then having all the code around it be generated, but have that pluggable if I ever want to replace that. The resulting code, just to be clear, is board specific in this case. So this needs to run on a Cortex-M. Your options there are, you can directly use a board package. So we have a list of supported boards in the Rust embedded working group. You can use RTFM, which is a small real-time scheduler for small devices and a framework to build safe devices there. Or you can use a full embedded operating system built in Rust, which is TalkOS. Or if you actually need full support for the board and you can't fill the holes yourself currently, but you want to write in Rust, you can just use a C-based operating system and like Riot and use that one. The final thing that's missing for that is Rust can be used to interact with C and C++ just if it were C. So, for example, you can generate static and dynamic libraries which provide you punctual speedup of larger programs, or if you have a device driver that's in C that you don't want to rewrite in Rust, you can just call into that device driver and use that one. It is also often used, for example, in mobile use cases. So if you want to deploy something on multiple smartphones and where usually C was used, you can just use Rust instead. I'm not going to go into detail here. Basically, what it ends up with is we can generate libraries that externally look like they are a C library, and then reuse all the facilities that we have. So for example, this is a piece of Ruby code that would use the previous library as a dynamic library, just load it, and allocate data, deallocate data through that library instead. So you can use Rust as a memory-safe C replacement. So in the cases where you would usually, for example, use a dynamic language, then say, well, we would rewrite it in C if it becomes slow, but then you suddenly threw all the memory safety that the dynamic language gives you out of the window. If you use Rust instead, that works as well. There's generators for that. So if you don't want to handwrite all of these, you can use generators for going from a Rust program to a C header, from a C header to Rust bindings. There's specialized tools just for Python, Ruby, and Node to make this conversation less rote and actually just auto-generated. Can also use a Rust program to, for example, compile to WASM. Because of time, I'm actually not going to talk about WASM. It's pretty much the same. It's a shared library by a different name. You can talk to me about that later. What's missing, especially when we're talking about bare metal, is safety critical use cases. We have currently no certified compiler, but we have recently started a project called Sealed Rust that attempts to bring certification of Rust on track. The problem being the language moves forward, so we need to at some point decide, okay, we're going to take a little piece of it, or we're going to take the current version and try to get it certified and actually keep it stable and supported for users that actually need that. But we got that on track. That's a multi-year effort, though. So, let's go back to these claims of performance. And so we have a language that's as fast as C and C++, with safety while doing the fast thing and abstractions with almost no overhead or no overhead. But also a language that cares about reliability by letting you express abstract concepts, making illegal states inexpressible, and with type-level support for resource management. And for productivity, we have great tooling. We check that every year. People usually give us 4 to 5 out of 5 stars. We have very good documentation. You can find that on our website, rustlang.org/learn. It's actually, we have extensive docs. We have 9 books written on all of these special use cases. So there's a book on the language. There's a book on embedded specifically. And we actually have a language, it's hard to present, that's well feasible for performance refactoring. So you can just do things a little wasteful, and then after it works, start refactoring to using more performant techniques. So does that work? We're seeing Rust used in many, many ways. And interestingly, we got roughly 33% influx, so a third, from functional language, dynamic languages, and systems programming. So people are coming from all, like, up the stack, down the stack, from all areas into the Rust project, because they're seeing that there's finally a language that they can kind of amend to their use cases easily, and it's well supported, and they can get stuff committed to the tooling to actually support that without forking off the little language community. Also, one thing you should consider, I'm actually not asking you to switch languages. I think there's a huge problem that if we bring new languages on the table, many people are like, oh my God, I need to get everyone retrained and all the stuff rewritten. No, that's actually not the case. This is why we offer these things like you can rewrite a small piece of it and then use Rust as a shared library, or you can integrate it. Bringing another tool to the belt on an organization level is much cheaper than actually like rooting for bringing the old stuff out. That's important to consider. And Rust is a tool that you can actually use everywhere. So it's a very useful tool to have. Might not be the thing that you use everywhere. But for example, if you are working, for example, in the IoT sector, it's one of the rare languages that can actually cover all of the use cases that you have, from small devices up to your server systems. So the conclusion is Rust is a language with well-chosen compile time guarantees and simple runtime semantics, and this simplicity is important because that allows you to use it in any area of your product, because you can build on these simple semantics towards the thing that you actually need, instead of dragging all of those semantics in the first place. So, thank you.